Hi, I'm Ethan Armis, and this is the first lab of Physics 2, the tape experiment. This lab was constructed for the purpose of observing Coulomb's law and calculating certain aspects of it, including the electric field and electric force. The pertinent laws and equations that relate to this experiment are, of course, Coulomb's law, which describes the electric force of one charge acting on another charge at a certain point, the electric field, which describes the electric field produced by a charge at a certain point, and static equilibrium, which is the principle that the net forces acting on a system sum to zero if that system is not moving. In this experiment, the system is a charged piece of tape, which we use in 3 different trials. The surroundings in the first trial is your hand, where we take the piece of tape and rip it off of another piece of tape and then hang it from the table. And as we move our hand closer to the table, we get to observe the electric force be applied as the electric field of the tape induces a temporary dipole in our hands, causing them to attract. The tape actually moved towards our hand. In the second part, it was a charged pin where we rubbed it with our shirt and moved it close. This caused a temporary charge to be placed on the pin, and it actually repelled from the tape. Since we knew that the charge in the pin was negative, we could conclude from this that the charge in the tape was also negative. Finally, the systems in this third part was another piece of charged tape, which we laid between 2 suspended portions and then brought our system charge tape close to it. Since they have the same sign of charge, they repelled each other, and using this information, we could calculate the charge on the tape. At the end of the experiment and creating a computational model, we found that the charge on the tape was approximately 1.14368 times 10 to the negative 8 coulombs, and that the ratio of electrons to atoms to be approximately 35.7 electrons per atom. In this photo, you can see the system tape suspended from 2 rulers and the surrounding tape which has been brought close to it. The like charges caused it to repel, and given the distance between the two when the tape began to bow upwards and it started to repel, which was about 2 centimeters, we could calculate the charge of the charge between the tapes. We did this by calculating the force of gravity acting on the tape, given that we have its mass, and then, since it's in static equilibrium, we can set that equal to the electric force. Rearranging this equation, we can solve for the charge, which, as I mentioned before, is about 1.14368 times 10 to the negative 8 coulombs. Here you can see the free body diagram, which we use to calculate the charge, and as you can see, we had to treat the tape as points, which means they are point masses and point charges. Here in the computational model, we made the same assumptions, and the computation actually ended up calculating the charge to be 1.2 times 10 to the negative 8 coulombs, which is close enough to our experimental value of 1.4 to support the experiment. However, as I mentioned before, we did have to make the assumptions that it was a point charge and point mass, and we also made the assumption that each tape had equal mass and equal charge. This could explain for some of the disparities between the values, but also in the experiment there were probably sources of error, which included the discharge while handling the tape, and that our mass calculation was not exact to the mass of the tape. So finally, we have some things to consider about the experiment. What if the electrons had a positive charge and protons had a negative charge? What would this change? This change would not affect the calculations of the lab, since protons and electrons have the same magnitude of charge. Opposites attract and same charges repel, so even if they were to switch signs, the same particles would attract and repel, so nothing would change. Finally, why is it important to handle the charge tape as little as possible? What happens when they come in contact with your hands or other objects? I touched on this earlier in the sources of error. This is important so that we keep the charge of the tape as consistent as possible, because when the tape touches anything else, it will begin to discharge and lose the temporary charge that it had. We want to do this so that our calculations can be as accurate as possible. So in conclusion, this lab demonstrated how with simple measurements you can calculate more abstract metrics of an electric experiment. In a future version of this experiment, one should take into account how the mass and charges of the tape are distributed along it and not just make the assumption that it is a point.